So today's lecture is going to be on something called the derivative. We're actually going to be on this topic for quite some time in this class. It's a really important topic in business calculus. So first we need to get some definitions out of the way. A tangent is a line that intersects a graph only once. And so if you had a curve like this, there wouldn't be just one single tangent. There could be really infinitely many tangents. It would all depend on where you were looking on the graph. So for instance, if you were looking at this point, this would be considered the tangent at that point. But if you moved over here on the curve here, then the tangent line would look like this. And notice those aren't the only two spots I could have put that on the curve, right? But then we can talk about the slopes of these lines. And notice the two lines that I drew over there to the left, there's definitely different slopes from each other, right? But in general, the formula for slope is, or rate of change is y2 minus y1 over x2 minus x1. And we're going to compare that today with the secant, which a secant is a line that intersects a curve twice. And both of these have real significance in calculus. So if we had another curve, like maybe a parabola, if we wanted to discuss the secant, we would need 2 points. And it would just be the line that crossed through those 2 points. Notice this wouldn't be the only secant I could draw as well. Like I could move the points around and the secant line would look different. Alright, so I'm going to refer back to those pictures throughout this lesson. But the first derivative, which is what we'll be discussing today, of a function f of x, we're going to write that from here on out. Instead of having to write out first derivative and all that, the notation is f and then a little kind of 1 or little slash mark there. You read this as f prime of x. Okay, so what is it? What is the derivative that we're trying to find? It turns out that it is the equation for the slope of the tangent line at any point. So I'm going to say at an indicated point. So when you're being asked to find the derivative, it is the slope of the tangent line at an indicated point. Okay. Notice that would be a bit of a challenge with a curve like this one that I'm pointing at up here, okay? Because the slope of that tangent line, it would depend on which point I was talking about, right? Because the slope here is much different than the slope is here. Okay, but the derivative will get us the equations for all the slopes, basically, at any point we would want to choose. So remember back in 10.1 when we did the limit of a difference quotient function? And I told you that that equation had some significance. Well, it does, okay? And it's because it's how you find the derivative. So that limit of a difference quotient formula is the equation for derivative. And later on throughout this lesson, we're going to refer to this not just as a rate of change, but more specifically as an instantaneous rate of change. That's just a really fancy way of saying a rate of change at any given time. Okay, at any point or at any given time. So the formula for finding derivatives is kind of lengthy, but we've already kind of practiced that this semester. But the steps for finding f prime of x are as follows. The first step is we're going to find f of x plus h. So we're trying to find this whole big mess of an equation right here, and we're just going to split it up into manageable pieces. Once we've done that, we're going to use that to find f of x plus h minus f of x. Notice I'm getting just a little bit more of the puzzle up here, right? The third step will be to take the previous step, so whatever information you get there, and we're going to put it over h. And then last but not least, I'm going to put a star by this one because this is the whole thing together. Okay, so finally we're going to find the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so those of you who are really algebra confident may be able to kind of skip to that final step and kind of condense and combine some of those first three steps, but I'm going to show all the steps kind of worked out because I think, especially at first, some of us need that. So let's look at finding the derivative of maybe a pretty simple function like 2x minus 7. So when you're asked to find this, okay, the formula for derivative is that long limit of a difference quotient. And you're going to find that I'm going to write this down on every problem. The more often you write this in your notes, the more you'll be able to commit it to memory so that you'll know it for the first exam. All right, so the four-step method just simply takes an ugly equation and just breaks it up into manageable pieces. So the first thing we're going to do is find f of x plus h. Well, f of anything means go up to f and replace x with that parentheses. So notice we have the 2 being multiplied by both things. So if we multiply and do distributive property, we'll get 2x plus 2h minus 7. Okay, there's no like terms there, so that's as far as I can go with step 1. Step 2 is to take what we got in step 1 and subtract off what we get when we take the original function. So here was my f of x plus h that I got in step 1, and I'm going to subtract off the original function, which was just f of x. Notice that when I do that, I will have a minus sign distribute to both things here. So this is 2x plus 2h minus 7 minus 2x plus 7, right? Because minus a negative becomes plus. So here we'll get some terms that will combine because they're alike. 2x minus 2x is 0, negative 7 plus 7 is 0. And it looks like all we're left with in step number 2 at the end is 2h. So you take each step as far as you can go, and then you're going to use the last step to move on to the next step. So notice this step starts with this and just divides it by h. So I'm going to take 2h and I'm going to divide it by h. That's what step 3 involves. So notice this one's relatively nice, right? The h's go away. So at the end of step number 2, I'm simply left with 2. So I'm almost there. Now my final step is to take the limit of whatever it is I got from step 3. So if I want the limit as h approaches 0 of 2, when you have a limit of whole numbers, notice normally we would try to plug in the 2 for h here, but we don't have an h to plug in 0 for, so the answer is just strictly 2. So in the end, the equation for the tangent line, or the slope of the tangent line rather, is 2. Okay. Notice this is a kind of an uninteresting one. We wanted the slope of the tangent line, but if you go back up and look at the original equation was 2x minus 7. It's linear, right? So the slope of a line that's 2x minus 7 would always just be 2. Okay, that's where we would find the slope. So it's kind of no surprise that we got 2 as a slope. But that's why I say that problem's really not that interesting. The slope actually stays steady at 2. So let's do one where maybe the slope would not stay the same. So if f of x equals x squared plus 2, let's do the same thing. Let's find the derivative. Okay, remember, derivative notation looks like that. So maybe not totally necessary for this problem, but I want to sketch the graph of this just real briefly. X squared equations look like parabolas. This parabola has been shifted upward 2 units. So it looks like this kind of curve. So all I'm trying to say is if I asked you to find the slope of the tangent line, you would need more information than that, because here's a tangent line. You could find that slope. But here's also a tangent line, and you could find that slope. Okay, so you could draw lines kind of all over that curve. Okay, so this one is going to be a more interesting answer. So again, if I'm asked to find the derivative, that is this limit of a difference quotient equation. Just maybe a side note, if you have taken a pre-cal or calculus class somewhere else and you already know the shortcut for derivative, we're not going to be able to use that here, okay? And there is going to be problems on the test where you have to use this definition rather than the shortcut. So if you don't know what I'm talking about, you can ignore that statement. But if you know the shortcut, just keep in mind I'm going to ask you to do it this way, at least for a little bit. So let's go through our stages. So first we'll start with f of x plus h. This is often the most tedious step of the whole process, because it often involves FOIL and all that good stuff. So we have x plus h times itself, and then plus 2. So remember, we talked about this before. Don't try to distribute the squared. You can't do that when you're adding. But if you do FOIL, you're going to get x squared. You'll get xh from the O step. You'll get another xh from the I step. That's a total of 2 xh's. Plus h squared plus 2. So I kind of combined my O and I step right away there just to save some time. So no like terms, so I can move on to step number 2. So step number 2 is to take what I got in step number 1 and subtract off f of x from it. So I have x squared plus 2xh plus h squared plus 2 minus the original function, which was x squared plus 2. So don't forget that this minus sign, again, just like in the last one, goes to both things there. So we get x squared plus 2xh plus h squared plus 2 minus x squared minus 2. So in this step, you're almost always going to get some terms to cancel out. So x squared minus x squared is gone. 2 minus 2 is gone. And what's left is 2xh plus h squared. Okay, so that's step number 2. Step number 3 is take what we got in step number 2, which was this, right? And we put all of it over h. So what happens when we put 2xh plus h squared over h? So remember, we can only cancel terms when there's an h in everything. One way around that is to say, hey, the top has an h in common, so if I factor that out, I'll have 2x plus h left. And then I can simply just cancel the h's out. So I end up with 2x plus h. So I'm almost there. So the last step is to take everything you just did and find the limit as x approaches, or as h approaches 0 of it. So in other words, we're going to do the limit as h approaches 0 of what we just found in step 3, which was 2x plus h. So notice here, up here, everywhere else, we would have had a problem with getting 0 on the bottom. Notice here we no longer have a denominator at all, let alone worry about 0 there. So here we're going to plug in h equals 0. And notice that once we do, we get an answer of 2x. So how we would write this with our notation is f prime of x equals 2x. Okay, so let's talk about what that means, because that's a little more interesting of an answer than we got in example 1. This means the equation to find the slope of the tangent at any point at all is 2x. Okay, and the reason it's an equation instead of just a plain old number is because that slope would change depending on what the x was. So I'm going to kind of add a part B here. So I want you to take this information. I just told you that was the equation for slope, and I want you to tell me what is the slope of the tangent of f of x equals x squared plus 2 for the following. I want you to find the slope if x is 4, if x is 0, and if x is 3. Let's go -3 actually. Okay, now we already looked at the parabola, right? Those slopes should be different from each other. If you look at that parabola, the slope is steeper the further out from 0 you go. But we have an equation, luckily, to find slope. Whatever our x is, we can just plug in here, and that will tell us our slope. So for x equals 4, the slope is, we always use the letter m to represent slope, right? So it's going to be 2 times our x value, which is 4, or 8. If x is 0, the slope is 2 times 0, or 0. Okay. In other words, at x equals 0, the tangent line is just a horizontal line. It has no slope at all. And then lastly here, if we plug in -3, we get -6. Okay, so here the slope is negative. Okay, so if you look back at that graph, maybe you'll see some of that. So as we kind of move the point around that function and draw a tangent line there, the slope definitely changes as we go. But this 2x equation describes the slope at any single point. Alright, so I call today's lesson kind of algebra heavy because there's just a lot of little algebra mistakes you can make. So you'll just want to be really careful on the more complicated ones, that you do FOIL correctly, that if there's a negative that you treat that accordingly, and so on and so forth. Alright, so let's do one more, and then we're going to look at something different. So if g of x is 2x squared minus 5x, find g prime of x. So remember, the formula for g prime of x is that big old long difference, or limit of a difference quotient. So we're going to do this in stages. G of x plus h is going to be 2 times x plus h squared minus 5 times x plus h. So my first suggestion is to, just like we did in the last one, rewrite x plus h as something times itself. And then let's do FOIL. Notice, if you pay attention, you already did x plus h times x plus h in the last problem. Okay, and you're going to have x plus h squared a lot, so if you can kind of commit to memory what that is, you don't have to do FOIL every single time. You can just kind of repeat. But remember, if you do FOIL, this is what you get. Okay, so all I did in that step is FOIL the x plus h out. But now I have kind of a series of distributive property, right? Everything's going to get doubled, and then everything gets multiplied by -5. So I get 2x squared plus 4xh plus h squared minus 5x minus 5h. Kind of a long list, and notice we don't have any like terms, so This is as far as we can go with step 1. So in step 2, we move on and we take step 1 and we subtract g of x from it. So we're going to have 2x squared plus 4xh plus h squared minus 5x minus 5h, and then minus the original function. So rather than writing out another step, I'm just going to kind of in my head realize that these signs are going to change. So I'm going to have 2x squared minus 2x squared. That's gone. I'm going to have minus 5x, and then minus a negative is going to change to plus, so that's also gone. So I will have left 4xh plus h squared minus 5h. Okay, so step number 2 is done. Step number 3 is to take what you got in step number 2, but divide it all by h. So 4xh plus h squared minus 5h all over h. So again, let's factor that out of the top, or factor an h out of the top, so that would leave us with 4x plus h minus 5 in the parentheses over h. And so if we cancel the h's out, we will get 4x plus h minus 5. Notice the process is a little slow going, but like with every step it should be getting kind of smaller and smaller. We should be able to simplify and condense more and more. So I'm going to put a star by this one. This is the finale. This is what we're looking for in the whole problem. Steps 1 through 3 were just the middle stages to get there. So now I want to take the limit as h approaches 0 of what I got in step 3. So notice now that the denominator's gone, I'm free to just plug in 0 here. So plug in h equals 0. And so in the end, I just get 4x minus 5. So make sure you know how to write this. So the derivative of g was 4x plus 5. Okay, and once again, this describes the equation for the slope of the tangent at any point at all. So depending on what the point is, that would change what the slope was. Okay, so let's do a part B to that one just to make sure. So what if I told you to find the slope at the following points? 0, 0, or maybe 1, 7. Scratch that. It would actually be at 1, negative 3. Sorry about that. Alright, so let's start with the first one. I want the slope. Notice here's an equation for slope and it has an x in it. So the only part of this I really need for this problem, I just need to know what the x is. So x is 0. So the slope is going to be 4 times 0 plus 5. We're plugging it into this slope equation. So we're going to get a slope of 5. And then for the point 1, negative 3, again, we really just care about the x value. So if we plug in 1 and we do 4 times 1 plus 5, we'll get 9. Okay, so what those results tell you is that the rate of change here is much steeper or higher than the rate of change here. Okay, so the tangent line is a steeper line than, at 1, negative 3 than it is at 0, 0. All right, so remember, the 4-step process is just really intended for you to keep your details straight. If you are more algebraically confident and you feel pretty good about showing your work and just kind of condensing steps 1 through 3 and kind of skipping straight to step 4, I'm okay with that, but I'll just say make sure that you know how to show your work. Okay, make sure you're not trying to use a shortcut or something like that, because I can almost always tell the difference when I grade your tests. All right, so derivative is the slope of the tangent. And remember, slope in general just means a rate of change. So the derivative measures a rate of change. So I mentioned at the beginning of the lecture instantaneous rate of change, and we're going to compare that with another type of rate of change. So the formula for instantaneous rate of change is the same one that we use for derivative, because the instantaneous rate of change is the derivative. Okay, so the instantaneous rate of change is talking about, again, the slope of the tangent line. So what's the slope of that line that hits the graph only once at a specific point? But let's talk about like a real life example of instantaneous rate of change. So if you look down at your speedometer at any given time, your speed, the second you check your speedometer, is your instantaneous rate of change. So it's the speed your car is traveling at a given time. So let's say you have a 30-minute commute, and 10 minutes in you look down at your speedometer and you're going 75. Okay? But then 20 minutes into your commute, there's been a little bit of a slowdown, so you're only going 60. Okay, so notice the instantaneous rate of change is not the same at minutes 10 and 20. Okay, it could be, but in that case it wasn't. So we're going to compare that to something kind of closely related, but average rate of change. Okay, so I'm going to give you the formula for that in a minute, but the difference here is instead of it being the slope of the tangent line, it's actually the slope of the secant line. So instead of it being the slope at one point, it's actually going to be the slope between 2 points, because remember, secant lines cross the graph twice. And it turns out the formula for that really should look familiar to you. It's f of x plus h minus f of x over h. So compare that with the formula for instantaneous rate of change, and notice it's just missing one thing, right? It's missing the limit stuff. Okay, so if you were doing the 4-step process to find derivative, you need the 4-step process to find instantaneous rate of change, but you only need to go to the 3rd step, because remember the 3rd step is this exact equation. The 3rd step will give you the average rate of change. So let's go back to our commute. The average speed of your car would be your average rate of change. So the average speed of your car during your commute, that would be describing your average rate of change, right? Because if your average speed on your 30-minute commute is 70, that does not mean you were going 70 steady the whole time, right? It just means probably sometimes you were going faster, sometimes you were going slower, but overall your average was 70. So often these average rate of change problems look a little uglier than they should. So we're going to try to just break down what it's asking for. We're going to look at a couple. One just straight up average rate of change problem, and then maybe another one where we use some application. So if f of x equals 3x squared, I want you to find the following. So we're just going to go through a couple of things. So the first thing would be the slope of the secant. So my question to you is the slope of the secant, are they asking you for instantaneous rate of change, or are they asking you for average rate of change? Okay. Notice it's the slope of the secant, right? So the slope of the secant is average rate of change, so we're supposed to just be doing f of x plus h minus f of x over h. We don't need to do the limit portion. So when I go to try to find that, I can just do steps 1 through 3 instead. Again, if I told you if you're algebraically confident, you might be able to skip some of this, but if you have 3 times x plus h squared, so I'm using 3x squared here. So again, we're going to have 3 times x plus h times itself. So remember what I said, you can use previous problems to do the FOILing, because the FOILing is the same. But in the end, you should get 3x squared plus 6xh plus 3h squared. Okay, no more like terms, so that's as far as we go with step 1. Step 2, we're going to do f of x plus h minus f of x over h. Sorry, I've skipped a step, right? So not over h, right? Just f of x plus h minus f of x. I was trying to skip down to step number 3. So for step number 2, we'll do 3x squared plus 6xh plus 3h squared minus the original function, which was just 3x squared. So notice what's going to happen here. My x squareds are going to go away, or my 3x squareds rather. So I'm left with 6xh plus 3h squared. And then my last step, it's my last step because I don't need to do the 4th step, because when I'm finding average rate of change, I don't need the limit portion. So that just involves me putting what I got on the last step over h. So we can shortcut this as long as you remember to cancel an h out of everything. H goes away there, but also goes away here. So we're left with 6x plus 3h. And that's as far as we can go. Okay, this is the slope of the secant line. Okay, notice we weren't given what x is, nor were we given what h is, so that's as far as we can go. If we were given one of those things, we could plug it in, but we weren't. We don't plug in h equals 0 because we're not doing that limit step for average rate of change. All right, so what about this question? What if I told you to find for me the slope of the graph at 1 comma f of 1? Okay, don't let this throw you off, this notation. MyMathLab, I mean, will show you a couple of these. Don't let that throw you off, like this is your x and this is your y. This just means to get the y, we're going to plug in f of 1, or we're going to plug in 1. So if you want to, you can go ahead and find out what f of 1 is. Okay, just plug it into the original, right? 3 times 1 squared would be 3. So what they're really asking you for is the slope of the graph at 1, 3. Okay, notice this is the slope of the secant, right? So that's not quite what would give us the slope of a single point. For that, we need instantaneous rate of change, right? So to find the slope at any point, we need to do the limit as h approaches 0 of f of x plus h minus f of x over h. You might groan and say, oh, I don't really want to do that, but actually we already did all the hard work, right? We already figured this part out here. We got to step 4, right, or step 3. We just need to do step 4. So the limit as h approaches 0 of 6x plus 3h. Notice now we do plug in h equals 0. So if you're asked to find the slope equation, that would be 6x. I'm going to circle this. This is not my final answer. This is the slope equation. But that's not exactly what I was asked to find in this problem. I was asked to find specifically the slope when x is 1. So let's do that. So the slope when x is 1 is m equals, where's my slope equation, right? 6 times whatever x is. So 6 times 1, or 6. And then last but not least, you might see this on MyMathLab. I want you to find the equation of the line through the point 1, f of 1. I'm trying to word it like I'm pretty sure MyMathLab words it. just so you're not surprised. So for this, you're going to need just a bit of review from algebra. So remember, when we want to find the equation of a line and we have a point given, we use this point slope formula. And we need two things to use that formula. We need the slope, which we have, it's 6. And we need the point, and we found that above too. What was the point? 1, 3. And then we just plug it in. It's y minus the y value equals the slope times x minus the x value. So if we do distributive property, we'll get y minus 3 equals 6x minus 6. And then last but not least, we'll just add 3. So we end up getting y equals 6x minus 3. Notice that's just the equation at the point 1, 3. We would have gotten a different answer if we would have been asked to find some other point, okay, or the line through some other point. All right, so let's do kind of a different looking rate of change problem. And then we're going to review really kind of an, not really unrelated, but kind of a different topic that you're going to need going forward. All right, so let's look at kind of a word problem. So if a revenue function is given to you as this, r of x equals 60x minus 0.025x squared. And let's say I told you to find the average rate of change. If sales drop from 1,000 units to 1,050 units. I guess not drop, sorry. If sales increase, sorry about that, from 1,000 units to 1,050 units. Okay, so when you see average rate of change, then that means we're using this formula, right? Average rate of change. The formula is f of x plus h minus f of x all over h. Just so you know, this is just a really fancy slope formula, okay? This is just the change in y over the change in x. And so I think something that might help us on a calculating problem like this is to actually know what h is. H in a problem like this represents the change or the difference. In other words, it's the amount of the increase. Okay, so what was the amount of the increase in units? Here, notice h would be the difference, so it would be whatever we get when we subtract 1,000 from 1,050. So here h is 50. So if I want the average rate of change, what I'm really looking for is change in y. Well, in this problem, y is revenue. So I'm looking for r of 1050 minus r of 1,000. That would be the change in revenue. Okay, in other words, plug in 1,050 and find out what that revenue is. And then we'll subtract off what we get when we plug in 1,000, and then we'll divide that by h, which in this case is 50. So we just need to use our calculator to figure these things out. So r of 1,050, here's r, right? So we do 60 times 1,050 minus 0.025 times 1,050 squared. So let your calculator do this. It's $35,437.50. Okay, r of 1,000 is going to be the same exact equation, but replace 1,050 with 1,000. So this one comes out a little more pleasantly, 35,000. So if I want the average rate of change, and I do, now I just need to plug these values in. Okay, here's my formula, right? So I take the $35,437.50 minus 35,000, and I divide that difference by 50. And so if you punch this in your calculator, you're going to get 875. Always make sure you put the unit. This is talking about revenue, so it's going to be in dollars. So in other words, we're changing the revenue by $8.75 per unit when we increase production from 1,000 to 1,050. So I hope you'll kind of look back over examples 4 and 5, kind of two different ways to think about average rate of change, but in both cases we're really just looking at the average rate of change formula, which is the same formula we were using for derivative, just take off the limit portion. All right, so for the final question in this lesson, I want to review real quick, just because I'm not sure if most of you had Business Math 1 or if you took online college algebra for your first class. I want to make sure we know how to graph basic piecewise functions. We've been looking at piecewise functions over the last few lessons. And honestly, I forgot to review this in those lessons, so we're going to do it here. There's also a problem like this on your homework this time, because I really want you to have practiced this. So let's say you're given a piecewise function. Remember, those look like curly braces and then usually more than one equation. So let's say that f of x is x squared plus 1 if x is less than 0, but it's 1 if x is greater than or equal to 0. So hopefully you kind of know by looking, this first equation is going to be a parabola. So we have a parabola pattern, but then once we hit 0, we're a constant 1 pattern. So here's how you old school graph piecewise functions. And honestly, your graphing calculator isn't the most helpful because it doesn't graph pieces of functions, it graphs full functions. So what I do for these is I set up two different XY charts, one for each of the two pieces or parts. And then I kind of graph them as I go. So for this XY chart, I want to choose x's that are less than 0. Okay, so I can choose anything I want, but keep in mind I'm going to have to graph this, so I don't want to pick crazy big numbers. So I'm going to pick -2 and -1. Notice those are the first things I could think of that were smaller than 0. But I also actually want to include 0 itself. Okay, so I'm going to put a star by this point. The reason for that is I need to know where the open circle is. Okay, and the reason this is open, just so you know, is all the way back up here. The fact that this was a plain old less than as opposed to a less than or greater than means that's an open circle. So now what we do is we're using this equation and we plug them in. So if you square, remember when you square things, they become positive. So -2 times itself would be +4, plus 1 is 5. -1 squared is 1, plus 1 is 2. Even though it's open, we want this point, so 0 squared plus 1 is 1. So over off to the side, let's do a basic graph where we go out 3 in every direction. And let's graph these points we got. I don't think I went out far enough, right? I'm going to need to at least go up to 5 since I have a -2, 5. So I'm going to really over-exaggerate this. This 0, 1 is open. But then -1, 2, and -2, 5 are just normal closed circles. So notice, just like I expected, I have a partial parabola, right? Because the first pattern was a parabola until you hit 0, and then you're supposed to change patterns. So for the second chart, we're going to pick out things that are greater than or equal to 0. So we'll do 0, 1, and 2. Notice this time it's greater than or equal to, so this is actually going to be a closed circle at 0. So notice I included 0 in both charts because 0 was the turning point. But this is a very uninteresting function. We actually always get a result of 1. So interestingly enough, this doesn't always happen. This one, 0, 1, is going to come right on top of that open circle and go ahead and close it in. And then we have 1, 1, and 2, 1. And so just like we thought, notice this graph turns out to be a partial parabola and then a partial constant function. So just a couple of things to remind yourself if you learned this before, or maybe if you're learning it for the first time. I split this up into 2 different charts because I had 2 different equations to work with. So like this chart goes with the first equation, this chart goes with the second equation. I did that so I could keep really clear my different shape, right? Because on this side I have a parabola, on this side I have a horizontal line. So you will be expected to know how to graph piecewise functions. So I told you the first week that, if I thought we would need something, I'd kind of review as we go, and so that's what I'm trying to do here. So